AP Calculus AB, Unit 7, Day 3. Assignment, office hours. Should have tried these problems, check your answers already. And so we're going to try them out right now. So some of these questions in the front are kind of like some good review questions from the final. In your test next week, are going to have a lot of questions just like that from the final, not related rates. So it says 0 to pi, it's an open interval, x coordinate is the relative minimum interval where f of x is concave up. So we definitely need to find the first derivative. Derivative cosine is negative sine. Leave the inside the same. Chain rule says multiply by the derivative what's inside afterwards. Plus derivative of x is 1. I'm going to set it equal to 0 undefined to find critical points. So we're going to get sine 2x minus 1 divided by negative 2 is positive 1/2. Alpha is pi over 6, quadrants 1 and 2. So 2x equals pi over 6 plus 2 pi k. And 2x equals 5 pi over 6 plus 2 pi k. Divided by 2. Divided by 2. So x equals pi over 12 plus pi k. And x equals 5 pi over 12 plus pi k. And we want the values between 0 and pi only. So pi over 12 and 5 pi over 12. These are your critical points. So we can do a line check. First derivative test. Pi over 12, 5 pi over 12, 0 to pi, put in parentheses or brackets because it didn't say inclusive. We're going to test a point. I'm going to test x equals 0, plug it in the derivative. That's going to give you positive, negative, positive. I'm going to draw these little arrows, increasing, decreasing, increasing. So this is a relative max. This is a relative min. So we could say, it just says the x coordinate. So the relative minimum is at x equals 5 pi over 12. I'm not going to justify it. If I justify it, say by the first derivative test, and I have to go in the explanation of it. Part B says, where is it concave up? So we're going to take the second derivative, the first derivative. So that's going to be negative 2 cosine 2x times derivative what's inside times 2. Derivative 1 is 0 equals 0 undefined. So cosine 2x equals 0. So 2x equals, when is cosine equals 0? Pi over 2 plus pi k. No quadrants, no reference angles. X equals pi over 4 plus pi k, pi over 2k. And we want all the values between 0 and pi. So it would be pi over 4 and 3 pi over 4. Now these, I'm pretty sure these are inflection points because they're not going to bounce off the graph. Label your line check. Put these guys on there. Put your boundaries. Okay, so let's see, we're going to test x equals 0. That's going to be negative, positive, negative. This is concavity, so our little nose is concave down, concave up, concave down. This is an inflection point. This is an inflection point. So we want to know where is it concave up. So it is concave up on pi over 4 to 3 pi over 4. We never include the endpoint for concavity. So some good practice. Okay, on what interval is this graph increasing? So that means we're looking for the derivative to be positive when we do line checks. So we're going to take the derivative first. Now this is going to be a product rule. X times derivative e to the 2x is e to the 2x. Chain rule says derivative of what's inside. Plus e to the 2x times derivative of x is 1. So that equals 0 undefined. We clean it up. 2x e to the 2x plus e to the 2x. I'm going to factor it. So I'm going to factor out the e to the 2x. GCF. That can equal 0. This can equal 0 would be at -1/2. So this is your only critical point. So we could do a line check. Label your line check. I'm going to take off points if you don't label it. -1/2. There are no endpoints. Test point. X equals 0 will be in the derivative. This gives you, it's going to give you 1. It's positive. Positive, negative, decreasing, increasing, relative min. So we want increasing. So it is increasing on the interval -1/2 to positive infinity. Never include infinity. We generally do include the endpoints for increasing, decreasing, unless there's a domain issue, which we should be paying attention to right now. In fact, the very next problem looks like it could have a domain issue, right? Domain, the inside of a log has to be positive. So this is, we could just say, okay, x cubed equals 1, so x equals 1. And you can do a line check. This is a polynomial inequality, so the way we usually did those is with line checks. Those are the first things we did line checks with, I think. Test x equals 2, it's positive, it's true, it's false. So this is the domain. We can only include answers greater than 1. So watch out. Yep. So inflection points, we're going to do first derivative, which is 1 over what's inside, times the derivative of what's inside. So we get 3x squared over x cubed minus 1. And the second derivative, I'm going to do quotient rule, low d high minus high d low all over low squared. Now, I'm going to set this equals 0 and define. I think we should clean this up first. So it's going to be 6x to the 4th minus 6x minus 9x to the 4th. Bottom, leave that factored. And we can take even further, negative 3x to the 4th minus 6x. And then we could factor the top, take a negative 3x out. This would be x cubed minus 2 equals 0 undefined. Now the undefined comes from the bottom, which gives you an answer, 1. The 0 comes from the top, which gives you two answers, x equals 0 and x equals the cube root of 2. So we have all of those. Well, hold on. This is supposed to be a plus, so this is negative. Okay, so those are all critical points. You got to watch out for the one on the bottom that's squared, so it's going to bounce off the graph. So inflection points, we don't really need to do a line check. It's got to be something where the concavity changes. A bounce isn't going to change, so it would just be these two. Find the x coordinate. And so you would say, we would say that the inflection points are at x equals 0 and negative cube root of 2. Okay, right? You wouldn't say 1 because 1 repeats itself, but here's the deal actually. we should only consider answers that are greater than 1. That's the domain, right? And none of these are greater than 1. So the answer is actually none. None. Now, if you were to do a line check, just not that you need to on this, but just to demonstrate, negative cube root of 2, 0, 1, test a point, x equals 2, I guess. I don't know. That'd be positive, positive, negative, stays negative, positive, negative, right? Concave down, concave up, concave down, concave down. Now, if there are no domain issues, you could use this, but this is it. The graph is concave down for its entire graph because it only exists when x is greater than 1. So watch out for domain issues. Okay, this is the graph of the derivative, okay? I'm going to try and find everything about the original graph from this. So the first thing I do is I say, okay, these are all slopes. These are positive slopes, negative slopes, positive slopes, increasing, decreasing, increasing, increasing, right? This is a critical point right here. This is a critical point right here. This is a critical point right here. It's going up and then down. That's got to be relative max. It's got to be a peak. If you're going down and then up, negative and positive, it's got to be a relative min. This is neither. It's plateau. It's going up, flattens out, goes up more. We can determine second derivatives from this graph, concavity, which would be slope of this graph. This is already the graph of the derivative, so the slope of this graph is the second derivative. So here f double prime is negative, concave down. Here f double prime is positive, concave up. Here f double prime is negative, f double prime is negative, concave down. And here f double prime is positive, concave up. It also means that this is an inflection point here, here, and here. So we have I think probably everything they can ask for. It has a relative max at x equals 1, right? It's decreasing on the interval 1 to 3, and we usually include endpoints for increasing, decreasing. Where this graph is negative, those are negative slopes. Increasing and concave down. So it's got to be going up and concave down. So it's concave down here. I'd say 0 to 1. Right, increasing concave down. Now, do we include 0? Not for concavity. Do we include 1? It is in the middle of concave down. And we include endpoints for increasing, decreasing. So that should be a bracket. And then I think there's probably some others. Increasing 4 to 5. Do we include it for 4? No, because it's the edge of concavity. You include it for 5? No, because it's the edge of concavity. So that's your answer. Inflection point at, you already wrote it down, 2, 4, 5. So we can get tons of information from the graph of the derivative. Now the next problems are some more optimization practice. So let's try these out. I think we are going to potentially run into some issues here where we can't do EVT, possibly, and we'll have to maybe try and resort to first derivative test, but only if you really have to, because it's pain. Okay, container with square bases, vertical sides, open top is made of 1,000 square feet of material. Find the dimensions of the container with the greatest volume. So the dimensions, greatest volume. So we need volume, which is base time, base area times height, which is x squared times the height. And we want to try and get more variable. The surface area is 1,000. The surface area would be the area of the base, and the area of all these sides. There's 4 of them, and they're each x times h. and they should add up to 1,000 square feet. What's going to be easier to solve for, x in terms of h or h in terms of x? X, you're going to have to do quadratic formula. It's going to be horrible. Let's go for h. So 4xh equals 1,000 minus x squared. You're going to divide both sides by 4x. So that's h. I'm going to plug that in up here. So the volume equals x squared times 1,000 minus x squared over 4x. Gives you 1,000 x minus x cubed over 4. We could keep going. This is 250x minus 1/4 x cubed. Okay, that's the volume. So we got to take derivative. Find critical points. 250 minus 3/4 x squared equals 0 undefined. So 3/4 x squared equals 250. Multiply by 4/3. So x squared equals 1,000 over 3. So we take the square root of both sides, plus or minus, plus or minus, plus or minus. I'm just going to leave it like that. I'm just going to leave it like that. That's fine. Critical points. Okay. We need endpoints. Okay. Well, could x be 0? Problem with x being 0 is that your surface area ends up being 0, right? And it's supposed to be 1,000. So we can't equal 0. It can get really tiny, and then h gets really big. What's the biggest x could be? Well, that would be when h is 0, which is okay. You'll still have surface area. It would just be a flat box. So h can equal 0. If you set h equal to 0 up here, and then you figure out what the x value is that does that, that's going to be when that equals 0. And it's going to be square root plus or minus. And so that's a positive square root of 1,000. So those are your endpoints. Sort of. But you don't have an endpoint here. So we technically can't do extreme value theorem now. We could kind of use a table to sort of figure it out. Justifying it is the problem. So here's the deal: you can't put x equals 0. You can take the limit as x goes to 0. Then this is gonna go to 0. It's gonna go to 0. It's getting tinier, tinier, tinier. And then the critical point would be the positive 1,000 over 3, and then the other endpoint would be the square root of 1,000. So if you plug these in, it's kind of gross. 250 times the square root of 1,000 over 3 minus 1/4 the square root of 1,000 over 3 cubed. If you put this in your calculator, which is probably our only hope, is 3042.903. If you do the square root of 1,000, we're going to get 1,000 out of it, and then we're still going to have a square, and then we're going to still have a square root of 1,000 left when we cube it. That's going to be 250. That's going to give you 0. So this is the max. But here's the problem. That was gross. What if you don't have a calculator? And technically, this is not extreme value theorem, so you can't really justify it with extreme value theorem. So you're going to have to, and you got to do it as a limit. So the other option is potentially use the first derivative test. Now, the first derivative test, you have negative square root of 1,000 over 3. We got 0. Well, 0 is your endpoint. Positive square root of 1,000 over 3 And I think we're going to go to the positive square root of 1,000 as your other endpoint. So if you test a value, x equals 0, and to v prime, you get positive. It's going up. And then it's going down. It's going down. So it is decreasing, increasing, decreasing. And this is a relative min. And this is a relative max. But realistically, it has to be in here. So we can tell that this relative max is going to be an absolute. Relative max is going to be absolute max. Now justifying is the hard part. You got to justify its relative max first. So you could say the greatest. Now here's the deal: if we take this approach, we never really found the greatest volume. If you did here, that's fine. But if we take this approach, we haven't figured it out yet. If we want to, we still got to plug this back in. But I think we can get away with it this time. The greatest volume occurs when x equals the square root of 1,000 over 3 feet, and h equals, so we haven't done h, we need to plug this in h. Did they say? Yeah, I have to find it. So we're going to plug the square root of 1,000 over 3 squared. That's 4 times the square root of 1,000 over 3. So this is a little messy. Okay, 3,000, so that's 2,000 over 3 times 3 over the square root of 1,000 over 4. It's pretty ugly. I guess it's gonna work out. Okay. We could take a 10 out and leave a 10 in. I guess we did times 100. 2 times 10. So we take that out. Just trying to make sure this makes sense. 1,000 squared. And then we could cancel that. So we have 200 over square root of 10. Or 200 square root of 10 over 10, or 20 root 10. This doesn't quite match the answer I got. But, okay. So I'm saying it's 20 root 10 feet. Since there is a relative maximum there by the first derivative test, for relative extrema, how? By v prime being positive on the interval 0 to the square root of 100 over 3, 1,000 over 3, and v prime is negative on the interval square root of 1,000 over 3 to the square root of 1,000. And since it is the only relative extrema, it must be an absolute maximum. So this is why you don't want to use this whenever possible. It's just a lot of explanation. But here you go. All right, keep this going. Cylindrical can, open on the top. This is kind of like one of those project problems, but it's a little different. It's open, so it makes a slight difference. Cylindrical can, you got R, you got height, can hold 500 cubic centimeters from the height and radius that minimize the amount of material to manufacture. So instead of having a set amount of material, we're going to try and minimize the amount of material. So that's surface area, which is it's open. So we just have a circle on the bottom, pi r squared plus, you open this up, it's a rectangle. And this right here is the circumference of the base. That's going to be 2 pi r h. We'd like to get this in one variable. So that's where the set volume, which should be pi r squared h equals 500 cubic centimeters. I think it's going to be easier to solve for h. H equals 500 over pi r squared. So plug that in up here. So the surface area is pi r squared plus 2 pi r 500 over pi r squared. Pi's cancel, one of the r's cancels. That makes it a little simpler. It's going to be pi r squared plus 1000. Let's say r to the negative 1, so I don't have to do question 1. So SA prime equals 2 pi r. And we're taking derivative with respect to r, 2 pi r minus 1000 r to the negative 2. So we write it with positive exponents and then give it a least common denominator. So that would be r to 2 pi r squared minus 1000 . Actually, this is supposed to be r squared. So pi r cubed. K equals 0 undefined. So r cubed equals 1000 over 2 pi, and you take cube root of both sides, no plus or minus. So I'll just keep it at that. It's a cube root of 500 over pi. That's a critical point. We could try and figure out if there's endpoints for r. Could r be 0? It's got to hold 500 cubic. No, if r is 0, your volume is 0. So you can get really close to 0. What's the biggest r could be? Well, that'd be when h gets really small. Can h be 0? No, it can't. But let's find the r that goes with that. So, well, as h gets tiny, r gets huge. So I really think that r goes to infinity. Possibly as h gets tiny. As r gets tiny, h blows up. Anyways, we don't have endpoints, so we can't do EVT. I mean, we could do it, we could figure it out, but if we had to justify it, it's going to be hard. And I'd say, well, let's take the limit as r goes to 0. And then we had cube root of 500 over pi, and then we'll take the limit as r goes to infinity. And we'll plug in the surface area, which was pi r squared plus 1000 over r. So this goes to 0. As this goes to 0, it blows up. It goes to positive infinity. The surface area goes to positive infinity. As r goes to infinity, that blows up, and this one goes to 0, but it still goes to positive infinity. And so then if we plug this value in, one of the reasons you might not want to do this is like really ugly. It's going to be pi times 500 over pi to the 2/3 plus 1000 over the cube root of 500 over pi. It's pretty messy. But the answer on your calculator, which would be the most realistic thing, would be 276.790. But the problem with that is it's not really EVT, so maybe we could do the first derivative test. So that we would have done all the work except for this little chart. So we got cube root of 500 over pi. Test point. R equals 0 because it's positive. It seems like the easiest. So it's going to be, that's going to be 0. R equals 0, that's going to be 0. This is going to blow up, but it's going to be negative. So I think it's going to be negative, positive, decreasing, increasing. This is a relative min. And because it's the only one, it has to be an absolute min. So we just got to figure out how to write this answer. We got to justify. So we say there is a relative minimum at, so let's find the height and the radius. So we still got to find the height if we do this, which is up at the top. This is ugly. So there's relative minimum at r equals the cube root of 500 pi, and h equals 500 over pi, cube root of 500 over pi squared. Okay. By the first derivative test, for relative extrema, since SA prime was negative on the interval negative infinity to cube root of 500 pi, and SA was positive on the interval cube root of 500 pi to positive infinity. So that that justifies the relative minimum. And you say, and since it is the only relative extrema, it must be an absolute minimum. All right. It's not fun, right? It's so much better when you do extreme value theorem. All right, on the back, we got another rowboat problem. So that warm up, hopefully yesterday, was helpful to you. A man floating in a rowboat 1 mile from the straight shoreline of a large lake. A town is located on the shoreline 1 mile from the point on the shoreline closest to the man. So here's the man. He wants to get to the town. He intends to row straight in a straight line for some point, and then walk the remaining distance. So he's going to walk. He's going to row. This is the best place to put x, by the way. Put x there, because then this is just 1 minus x, and this is the square root of x squared plus 1. So that's the best place to put a variable. It says he can walk 5 miles per hour, and he can row 3 miles per hour. Then we're going to do a different problem. Okay, so we want our time equation, which is, remember, d equals rt, so therefore t equals d over r. Time equals d over r. Distance, square root of x squared plus 1 over speed, right? Plus distance over speed. So this is your time equation. You might want to write it in a way that's easier to work with. The same thing as 1/3 x squared plus 1 to the 1/2 plus 1/5 minus 1/5 x. So t prime is going to be 1/6 x squared plus 1 minus negative 1/2 times derivative of what's inside, 2x. Derivative of 1/5 is 0 minus 1/5. So this is what we need to set equal to 0 undefined to find the answers. Now it's pretty ugly. So t prime equals, it's going to be x over 3 square root x squared plus 1. And minus 1/5. So we need to get least common denominator. So it's going to be 5x minus 3 square root of x squared plus 1 over 15 x squared plus 1 equals 0, undefined. Okay, so undefined comes from the bottom. I'm just going to give you imaginary this time. And then 0 comes from the top. So that's going to be 5x equals 3 square root of x squared plus 1. We're going to square both sides. It's going to be 9x squared plus 9. So it's going to be 16x squared equals 9. So it's going to be x squared equals 9 over 16. Square root of both sides, plus or minus, x equals plus or minus 3/4 for critical points. In points, what's the smallest x could be? Would be 0, and the biggest would be 1. So these are your endpoints. So we're going to make a table and plug it into the time equation. Okay, so negative 3/4, 0, 3/4, and 1. So we're not going to consider the negative 3/4. It's not between the endpoints. You plug 0 in, you get 1/3 plus 1/5. Least common denominator would be 8/15. 3/4 is going to be square root of 9/16 plus 1 over 3 plus 1/4 over 5. Now this is going to be the, if you give this least common denominator, it's actually, sorry, it's the square root of 25/16. Which is going to be 5/4, which is going to be 5/12 plus 1/20. So least common denominator be 3, or not 3, 5. And this one would be 3. So it's going to be 28 over 60. It's going to be 14 over 30 It's going to be 7 over 15. So 15 is okay. If you plug 1 in, it's square root of 2 over 3, which is approximately, I think it's like really, let's see. It's on your calc is 0.471, which is really close to this one, which is 0.467. And this is 0.533. So your max happened at an endpoint, or least time. So that's the max. And the min is right here. This is the min. So we are able to do EVT, which is nice now, after we had to do some problems that didn't have it. So the minimum time is, let's go with the exact answer, 7/15 hours when, now, I don't think we should say X, when rowing to a point 3/4 of a mile down the shore. Sure. By extreme value theorem. By checking endpoints and critical points. Right. Now, part B, the same thing, but we changed the rowing to 4 miles per hour. So a lot of it's going to be the same. The time function is going to be square root of x squared plus 1, but over 4 this time, plus 1 over x, 1 minus x over 5. So it's almost the same, just this one number right here changing. But we're going to have to redo all the work. So this is going to be 1/4 x squared plus 1 to the 1/2 plus 1/5 minus 1/5 x. We're going to take the derivative. It's going to be 1/8 x squared plus 1 to the negative 1/2 times the derivative of what's inside. Derivative 1/5 is 0 minus 1/5. We're going to say equal to 0 undefined. I'm going to go quickly here. I'm doing all the same kind of work, slightly different numbers. So this is going to be x over 4 square root of x squared plus 1 minus 1/5. And then gotta give these guys least common denominator. So you get 5x minus 4 square root of x squared plus 1 over 20 x squared square root of x squared plus 1 equals 0 undefined. So the undefined comes from here. This is going to be x equals plus or minus I, which we're not going to use. The 0 comes from up here. So it's going to be 5x equals 4 square root of x squared plus 1. I'm going to square both sides. You get 25x squared equals 16x squared plus 16. So we get 9x squared equals 16. We divide by 9. We take the square root of both sides, plus or minus, and we get 4/3 plus or minus as our critical point. The endpoints are the same as before, 0 to 1. And so then we got to make a table. X time equals square root of x squared plus 1 over 4 plus 1 minus x over 5. Endpoint 0, negative 4/3, which we're not going to bother checking. Positive, ooh, 1 positive 4/3 is also outside the endpoint. So we found these two critical points, but neither of them are between the endpoints. So really we just need to calculate the endpoints. It's going to be 1/4 plus 1/5, which would be 9/20ths, or as a decimal, 0.45. If you plug 1 in, you get the square root of 2/4. So we'd have to estimate that. Square root of 2 is between 1 and 9, which is the square root of 1 and the square root of 3. It's definitely closer to 1, so I mean, you might guess like 1.2. And that can be 12/40, which 2.5 times that, 24, 0.30, I think would be what that is. I mean, you could say 3/10, yeah, 3/10. So we're looking for the minimum time. So that's going to be your minimum time. Right. And then you got to justify it, which I'm not going to do right now.